we are using principal stresses. I repeat again, we are using principal stresses. So the energy, right, to deform the structure based on structure analysis, we know is 1 over 6G. And this will be equal to stress A squared minus stress A, stress B, minus stress B squared. Okay, so again, let me remind you, this is from structure analysis. And this has to be less than stress yield squared, okay, divided by 6G, right? So we bring this relationship down here. And you can cancel the 6G in the end, okay? In the end, we have stress A squared minus stress A, stress B, normal stress A, stress B, plus by stress B squared. It has to be less than stress U squared. Okay. Okay. So this is what we call von Mises criteria. So on the left-hand side, this is acquired from 3D mole circle with structure analysis. I will show you an example. Okay, this is now the theory, and over here, this is your material property. So in this context, right, now you have to realize that stress A and stress B are principal stresses. Okay, why we have to use principal stresses? Because the material property is under what? Uni-axial tensile test. Okay, when it's uni-axial tensile test, you only can get what? You only can compare the principal stresses from experiment. Okay, so the yield strength that I always remind you of, the yield strength that we get from any handbook is always what? Principal stress. Now, von Mises make another assumption. Yeah, von Mises is he make another assumption. So the assumption he make is von Mises also assume that the stress yield in compression is the same as tensile. Okay, he make or he make that assumption. Okay, so like rather than messing around, okay, thinking that there's too much theory going on, okay, I want to put this into action, okay, or not the topic can get really dry. Okay, so I want to do an example with all of you. Okay, then you can visualize better what is going on. So I've posted the example on Avenue to Learn, and I want you to load up the example. Okay, so the example looks like this. Okay, so this is our example number 1. Okay, this is a example number 1. So example number 1. Okay, so the 1.5-inch diameter shaft AB, you can see over here, it's made of great steel with a 42 KSI tensile use strength. So they give us a tensile use strength using, I'm going to change this. We're going to do both. Okay. First of all, we are going to use maximum distortion energy criteria. Determine the value of the torque. So we want to know what's the torque. When P is equal to 60 times 10 to the power 3 psi. Okay. So what is given to us is we are given that the diameter is equal to 1.5 inches. We know that the material will yield, okay, positive 42 times 10 to the power 3 psi. Okay. And we are given that P is equal to 60 times 10 to the power 3 psi. So we are going to apply, okay, we're going to use the maximum, okay, distortion energy, which states what's the maximum distortion energy, where we have stress A squared minus by stress A stress B plus by stress B squared must be less than our stress U. Okay. So we know the structure is under compression over here, and based on maximum distortion energy, the strain in tensile is equal to strain of compression, and this is equal to minus 60 times 10 to the power 3 psi. Right? Tensile and compression have the same value, and then we are going to use 3D Mohs circle, right, to determine the principal stresses, stress A and stress B. Okay, so now I'm going to draw our transformation. So I'm going to call this our X, Y, and Z. And we're going to look at which element to analyze. Okay, I know you have not seen any element yet. Okay, so we have to first carry out like what we have done before on the previous example. We have to carry out failure analysis. We have to carry out failure analysis. So if this structure were to break, right, the structure will likely break in this red region, okay, all the way around. Okay, it's going to break somewhere all the way around. So now if we were to have a view, right, we have a view. So this is my X. So we are going to view from the plan view, right? So I'm going to draw our structure looking from the plan view. Right. So I'm going to call this, or I'm going to now draw some center lines. Now this topic is not that difficult, okay? Compared to, I mean, last week the topic, or last lecture, the topic also was not that complicated. So now we are going to call this element I, element J, element K, and element L. Okay. So if we were to look at the loading condition, so we have our element first, I, J, K, and L. And if we look at minus Py over A, the normal stress, element I, J, and K all see the same, minus Py over A. And then if we look at the shear, which is equal to Ty x, or the radius, divided by J, all of them, okay, all of them have the same thing. So where failure will occur, it depends on where your impurity is, unfortunately. Okay, so every element is equally like stressed. Okay, I repeat again, every element is equally stressed. So you can pick any element. So for this case, let's say that we pick element I, for example. Okay, you can pick element J, K, is all the same. Okay, so if we were to pick element, select, you can select anything. Okay, you can select anything because the loading condition for any of the elements are the same. Okay, the stress magnitude are all the same. Okay, so we are going.
Eugene, how do you know they're the same?
Okay, same, 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 same.
How did you get the values, like the
Py is
negative?
constant. A is because Py is under what? Compression. Right?
Yeah.
Yeah, so it's all the same. Okay. There are cases that I've done last week. Okay, for this case. There are cases that I've done last week. For this case over here, they're not the same. If you look at element loading, they're not the same. This is last week. Okay, the loading conditions are not the same. Okay, for this week, this example, the loading conditions are all the same. So it does not matter which element we select. Okay, right. So from here, we just pick any element. So I want to pick our element I. Okay, so if I were to copy our transformation, okay, so element I, so this is my X, Y, and Z. Element I looks something like that. So we know element I, we have a normal stress in the Y value. And we also know that there's a shear because this thing is rotating this way, the torque, right? It's rotating this way. So the shear force will have that orientation. So this is our shear, right? This is our intersecting planes. X, Y is equal to shear YX. And the rest of the stress component are equal to 0. Okay. So from here, we can sketch our mole circle. The only value that we know for now, okay, the only value that we know for now is all. Let's try to compute stress Y. Okay. So stress Y is equal to Py over A. So Py, right, is equal to what? Minus 60 because it's under compression. Minus 60 times 10 to the power 3 divided by the cross-sectional area. Okay, so the diameter is 1.5 inch, 0.75 squared. this will be equal to 60 divided by shift pi divided by. It's 33.953 minus 33.953